All right, so moving on to 6.3. Okay, so in 6.3, I think you'll see why I take the approach that I take to solving trig equations that I showed you in 6.2. And it's because it makes equations like the ones that we're going to solve in 6.3 a lot easier. So once again, if you follow along with the way that your textbook does this stuff, they end up having to sort of introduce a completely new set of ways to like solve these kinds of equations. Notice that the difference here from what we were doing in 6.2 is that now we have more going on inside of the trig function, right? We're looking at stuff like sine of 3x equals 1/2 instead of just sine x equals 1/2. And so the book ends up introducing like a whole new set of ways to sort of solve these things. Whereas if you follow along with what I did in 6.2 and just apply those same techniques to 6.3 stuff, to equations like this, you're going to be just fine. So, so there's really nothing new here strategy-wise. We're just going to apply the same stuff that we did in 6.2, but now we have like this extra little bit of stuff to sort of take care of. It's really not that complicated. But once again, I'm going to show you the same examples that the textbook uses so that you can compare and contrast my approach to the way the book does it. And you're welcome to use whichever one you feel is, you know, better or easier for you to remember, or whatever the case may be. However, the first two examples I'm going to show you are not from the textbook. And then I'll go through the 4 examples that the textbook gives. Okay, so we'll do 6 examples in total, and the first 2 are not from the textbook. But I just want to show you the idea here. So let's say you have sine 3x equals 1/2. So this is already in that nice format that we were talking about in 6.2, you know, sine x equals k. And so what we're going to say is that, you know, if sine 3x equals 1/2, then if you were to take sine inverse of both sides, you would get 3x equals sine inverse of 1/2, right? That's one set of solutions, you know, and then every 2 pi units after that is also a solution. The other possibility is that 3x could be pi minus sine inverse of 1/2. I'm not sure why I'm putting parentheses there, but and then solutions every 2 pi units after that as well. Now the only additional step here is that in order to finish solving for x, you have to divide by 3. And now here's the key, because a lot of students make the mistake of saying 3x equals sine inverse of 1/2, and then they divide by 3 and they say x equals, well, sine inverse of 1/2 first of all is pi over 6, right? So they get pi over 6, and then they divide by 3 and they get x equals pi over 18. And then they stick the 2n pi on there and they say x equals pi over 18 plus 2n pi. That's wrong. You're going to be missing a whole bunch of solutions if you do it that way. You need the 2n pi on the very first step, because now when you divide by 3, you're going to divide pi over 6 by 3, but you're also going to divide 2n pi by 3, and so you get a lot more solutions. Okay, so really what you should get is, so this is pi over 6, by the way, so really what you're going to get is x equals pi over 18 plus, how do we want to write this? We'll say maybe 2n over 3 times pi, right? Because you have to divide both terms by 3. So that's one possibility. Or let's see, this is pi over 6. Pi minus pi over 6 would be 5 pi over 6. So 5 pi over 6. So we're going to get x equals 5 pi over 18, again, plus 2n over 3 times pi. Okay, so you get a lot more solutions. So if we were listing all of the solutions, they would just be those two. Okay, so it's these two sets of solutions where n can be any integer, right? So they both generate an infinite number of solutions. If you're interested only in the solutions that live between 0 and 2 pi, Now check out how many solutions you get, because our period has been divided by 3, right? So you're going to get 3 times as many solutions. If I plug in a negative number, like -1, pi over 18 minus 2 pi over 3 is going to be less than 0, so that's not going to cut it. But if I plug in 0, then I get pi over 18. Okay, so that's a solution. If I plug in 1, let me just use my calculator. I'm going to have pi over 18 plus 2 pi over 3. That's 13 pi over 18. Okay, and that's still less than 2 pi. 2 pi would be, what, 36 pi over 18. Okay, so we haven't quite reached it yet when I plug in 1. What if I plug in 2? If I plug in 2, I'll have pi over 18 plus 4 pi over 3. That's 25 pi over 18. That's still less than 36 pi over 18. Well, what if I plug in 4? If I plug in, what if I plug in 3? If I plug in 3, I get 6 pi over 3, or in other words, 2 pi. Well, 2 pi plus pi over 18 is obviously more than 2 pi. So if I plug in 3, then I've gone too far. But those 3 solutions are generated from this first rule. Now I'm going to get probably 3 more generated from this second rule, right? If I plug in -1, that's going to be too small. Right, you can try it out. 5 pi over 18 minus 2 pi over 3. But if I plug in, I just get 5 pi over 18, which is definitely in the interval. If I plug in 1 for n, I get 17 pi over 18. Right, that's still less than 36 pi over 18. If I plug in 2 for n, then I get 4 pi over 3 plus 5 pi over 18, and that makes 29 pi over 18. And then if I plug in 3 for n, I'll have 2 pi over 3, I'll have 2 pi plus 5 pi over 18. That's bigger than 2 pi. Right, so those are the solutions that I get. So notice that I have 6 solutions here that live between 0 and 2 pi. Okay, the big key is that you have to have the plus 2n pi on the first step. Okay, you have to have that there, so that then when you divide by 3, you're dividing this by 3 as well. Okay, so let me give you another example and see if you can apply that to the cosine case. So I'm going to give you 2 cosine 4x plus pi over 6 minus 1 equals 0. Okay, go ahead and give that a try. Okay, here's my solution. The first thing I need to do is isolate the cosine. So I'm going to add 1 and then divide by 2 to get cosine 4x plus pi over 6 equals 1/2. Okay? Now I can apply the rule for cosine, and I can say, okay, if cosine of this stuff equals 1/2, then that means the stuff equals cosine inverse of 1/2 plus 2n pi. Okay, so that's one possibility. Another possibility is that the stuff equals 2 pi minus cosine inverse of 1/2 plus the stuff, plus 2n pi, sorry. Okay, so let's simplify those. Cosine inverse of 1/2 is pi over 3. Okay. Let's see, pi over 3 and 2 pi minus pi over 3. 2 pi would be 6 pi over 3, so that's 6 pi over 3 minus pi over 3 is 5 pi over 3. Okay. And now we just need to solve for x. So to solve for x here, the first thing I would do is move the pi over 6 over in both cases. When I move the pi over 6 over, we combine like terms, okay? So pi over 6 and pi over 3 are both just constants, whereas 2n pi is a variable term, and so we're not going to subtract the pi over 6 from the 2n pi. We're just going to get pi over 3 minus pi over 6 is pi over 6 plus 2n pi, or 5 pi over 3 minus pi over 6, oh goodness, this would be 10 pi over 6. 10 pi over 6 minus pi over 6 is 9 pi over 6, which reduces to 3 pi over 2. Man, let me use my calculator to double check my math. 5 pi over 3 minus pi over 6. Yeah, 3 pi over 2. Okay. Good. So now then the last step to solve for x is to divide through by 4. And now here's where you do have to divide each term by the 4, right? So you're going to get x equals pi over 24 plus 2n over 4 would be, let me just show it. Right, so we're dividing by 4. And so that would be n over 2. That would be n over 2 times pi. Or x equals 3 pi over 8 plus n over 2 times pi. So if I were listing all of the solutions, that's what they'd be. Pi over 24 plus n over 2 pi, or 3 pi over 8 plus n over 2 pi, where n is an integer. If I were listing the solutions that live between 0 and 2 pi, I think that since my period here is going to be divided by 4, I'm going to have 4 times as many solutions as I usually do. Okay? Let's generate them. So I'm going to do pi on my calculator. I'm just going to do pi over 24. If, let's say, I plug in 1 for n, then I would have minus pi over 2. And that's negative. Okay? Yeah, that's negative 11 pi over 24, so it's a negative number. So that doesn't work. If I plug in 0 for n, then I'm just going to get pi over 24. That's in the interval. If I plug in 1 for n, then I'm going to have pi over 24 plus pi over 2. That's 13 pi over 24. Still in the interval. If I plug in 2 for n, then I'm going to have pi over 24 plus pi. That's 25 pi over 24. Still in the interval. Okay? Sorry, over 24. 2 pi, right? 2 pi would be 48 pi over 24. So I still have a ways to go before I reach that. If I plug in 3 for n, I'm going to get 3 pi over 2. That's 37 pi over 24, still in the interval. If I plug in 4 for n, well, if I plug in 4 for n, then I get 2 pi, right? 2 pi plus pi over 24 is going to be more than 2 pi, so that goes too far. So sure enough, I get 4 solutions generated from this first rule. From the second rule, a similar thing is going to happen, right? 3 pi over 8. If I plug in a negative 1 for n, I'm going to have minus pi over 2. That's negative. If I plug in 0 for n, I just get 3 pi over 8. That's definitely in there. If I plug in 1 for n, I'm going to have 3 pi over 8 plus pi over 2. That's 7 pi over 8. If I plug in 2 for n, 3 pi over 8 plus pi is 11 pi over 8. I shouldn't go beyond 2 pi, which would be 16 pi over 8. So I'm still in the interval. If I plug in 3 for n, I'm going to get 3 pi over 2. So 3 pi over 8 plus 3 pi over 2 is 15 pi over 8. That's cutting it really close, but it's still in the interval. So if I go one more, then I know I'm going to be outside the interval. Okay. And so those are the solutions there. Okay. So as you can see, like this is just the same exact kind of problem as what we did in 6.2. There's really nothing new here. The only thing is that, after applying this rule, then you have to still solve for x, so you still have to do some stuff. But that's really the only difference. So let me now run you through the examples that the textbook gives you. And so this next example is example 1 in the textbook. Okay, and it's 2 sine x over 2 equals 1. Okay, so go ahead and see if you can, so pause the video and solve this one on your own. Alright, here's my solution. So I'm going to say sine x over 2 equals 1/2. That means that x over 2 is sine inverse of 1/2 plus 2n pi, or x over 2 is pi minus sine inverse of 1/2 plus 2n pi. Well, sine inverse of 1/2 is pi over 6. Okay, so x over 2 equals pi over 6 plus 2n pi, or x over 2 equals pi minus pi over 6 would be 5 pi over 6 plus 2n pi. Now, this time in order to finish solving for x, you need to multiply through by 2, right? So if I multiply both sides of the equation by 2, I'm going to get x equals 2 pi over 6, that's just pi over 3, right? It reduces to pi over 3. Then 2 times 2n pi is going to be 4n pi. So notice that the period doubles in this case, okay? Or x equals 5 pi over 3 plus 4n pi. Okay, so if I want to list the solutions, if I want to list all of the solutions, it would be those two. And if I want to list the solutions between 0 and 2 pi, well, here, if I plug in a -1, obviously this is going to be too small. If I plug in 0, this is going to be pi over 3. If I plug in 1, that's going to be way too big. And then a similar thing happens over here. So I think pi over 3 and 5 pi over 3 are the two solutions that I get. And that's it for that. Okay? Let's do another one. Let's do cosine 2x equals cosine x. Okay, now here I'll give you a little hint. You want your you want to get this to look like the same, not just the same trig function, but you have to have the same argument. And so since here you have a cosine 2x and here you have a cosine 1x, you're going to need to find a way to reconcile those things. And so a double angle identity could come in handy. So go ahead and give the video a pause, see if you can work that out. Okay, so the double angle identity I'm going to use for cosine 2x is 2 cosine squared x minus 1. And the reason that I'm using that one instead of the 1 minus 2 sine squared x minus 1 is that then you're going to have mismatched trig functions, right? Or even worse, if you had cosine squared minus sine squared, you'd have mismatched trig functions. This way rewrites everything in terms of the same trig function. So now I have a chance of maybe being able to, move everything over in factor and then apply the zero product principle. Or if I can't factor, then at the very least I can use quadratic formula, right? We saw an example of that in 6.2. So anyway, without further ado, we have 2 cosine squared x minus cosine x minus 1 equals 0. Can we factor that? Yeah, I think so. 2 cosine x and let's see, so this needs to be a negative and a positive, so that way I can get a -2 cosine plus a cosine, and that'll give me a -1 cosine there in the middle. Alright, so that does it, right? So we're going to have 2 cosine x plus 1 equals 0, or cosine x minus 1 equals 0. So here we would get cosine x equals negative 1/2. Here we would just get cosine x equals 1. And then we apply our handy dandy little rule, right? We're going to say x equals cosine inverse of negative 1/2 plus 2n pi, or x equals 2 pi minus cosine inverse of negative 1/2 plus 2n pi. Okay, or right, or x equals cosine inverse of 1 plus 2n pi, or x equals 2 pi minus cosine inverse of 1 plus 2n pi. Whew. Had to cheat a little bit. That's more of a t than a pi, but okay. Let's simplify this. Cosine inverse of negative 1/2 is going to be 5 pi over 6. No, 2 pi over 3. 2 pi over 3, right? So this is going to be 2 pi over 3 plus 2n pi, or 2 pi minus 2 pi over 3. Well, 2 pi would be 6 pi over 3. 6 pi over 3 minus 2 pi over 3, 4 pi over 3, right? So x is 4 pi over 3 plus 2n pi. Here we're going to get what? Cosine inverse of 1 is 0. So we're going to get 0 plus 2n pi, or 2 pi minus 0. Now, this deserves a little bit of explaining, right? Obviously, 0 plus anything is just that same thing. X equals 2n pi. But here, I'm going to go ahead and claim that this set is the same as this set. Because if you think about the angles that are generated by 2n pi, when you plug in 0, you get 0. When you plug in 1, you get 2 pi. When you plug in 2, you get 4 pi, and so forth, right? So it's like negative, like there's an infinite number, and then you get to like negative 4 pi, negative 2 pi, 0, 2 pi, 4 pi, 6 pi, 8 pi, and so forth. What does this rule generate? Well, it generates the same set, right? Like if you plug in negative 2 here, you're going to get negative 4 pi. When you add 2 pi, you're going to get negative 2 pi. What about if you plug in negative 1? You get negative 2 pi plus 2 pi is 0. If you plug in 0, you get 0 plus 2 pi is 2 pi. If you plug in 1, you get 2 pi plus 2 pi is 4 pi, right? So, so you're generating the same set here, right? You're generating like negative 2 pi, 0, 2 pi, 4 pi, 6 pi, 8 pi. Well, it's the same set that you're generating here, and so this is really just redundant, okay? So really you have these three possibilities. So if you're listing all of your solutions, we would say they would be solutions of the form 2 pi over 3 plus 2n pi, 4 pi over 3 plus 2n pi, and then just 2n pi, where n is any integer, right? Negative or positive whole number. So now if you want to list off the solutions in the interval from 0 to 2 pi, I'm just going to cut to the chase and let you verify this, but you should just get 2 pi over 3, 4 pi over 3, and then from here you're going to get 0, and that's it. Okay? Notice that in this particular equation that we just solved, we didn't end up having to do anything with the 2x because we took care of it using using an identity. Okay, so after we applied our little rule here, there was no addition, right, to get from this step to this step. There was no additional solving for x, right, because x was already by itself, I guess. Okay, here's another one. This would be so by the way, This one was example 1 from the textbook. This one that we just did was example 2 from the textbook. And now this one is going to be the exact same problem as example 3 from the textbook. And it's 4 sine theta cosine theta equals square root of 3. Okay. So let's talk about this a little bit. If we move everything over and then try to factor and apply the zero product principle, I don't think we're going to have much luck, because you're going to end up with 4 sine theta cosine theta minus root 3, and there's nothing you can really factor with that. So I think we're going to have to take a different approach. And remember, what we're really trying to do is we're trying to rewrite all of these trig functions just in terms of one trig function with the same argument. So for example, rewriting cosine theta as cosine of pi over 2 minus theta, that's true. Or sorry, rewriting cosine theta as sine of pi over 2 minus theta, that's a true statement, but it wouldn't help because the arguments would still be different. Okay. So so here's what I would suggest, just kind of as a hint. Notice that 4 times sine theta cosine theta is just 2 times 2 sine theta cosine theta. And hopefully that looks familiar to you. So go ahead and give the video a pause, look over your identity sheet, and see if you can rewrite this stuff as something, as just a single trig function. Okay, I'm gonna spoil it now. Right, this is just sine 2 theta, isn't it? Right? So 4 sine theta cosine theta is really just 2 times sine 2 theta. And now that's a lot more simple, right? We need to finish solving for the sine function. But now we can take sine inverse of both sides, and we're going to get 2 theta equals sine inverse of root 3 over 2 plus 2n pi, or 2 theta equals pi minus sine inverse of root 3 over 2 plus 2n pi. And the rest is history, right? We'll finish it out, but it's pretty easy from here. Sine inverse of root 3 over 2 is pi over 3. And then pi minus pi over 3, so that's 3 pi over 3 minus, so 2 pi over 3 over here. And now when we divide through by 2 in order to finish solving for theta, we're going to get pi over 6 plus n pi, or theta equals pi over 3 plus n pi. Notice that I'm again dividing this term by the 2 to get the n pi. So if you wanted to list off all of the solutions, well, it would be pi over 6 plus n pi, and pi over 3 plus n pi, where n is an integer. If you wanted to list off the solutions that live in the interval from 0 to 2 pi, well, you're going to get pi over 6 and 7 pi over 6 generated from that first rule. From the second rule, you're going to get pi over 3, and you're going to get 4 pi over 3 generated from the second one. Okay, and that's that one. Okay, one more solution, or solution, one more example, one more equation. Let's do tangent 3x plus secant 3x equals 2. Okay, now I'll give you a hint. Again, you need to try to rewrite this so that you're rewriting all the trig functions in terms of the same trig function, unless you can factor it somehow. But there's nothing really to factor here. Even if you move over the 2, you're not going to be able to factor this. So you need to use some kind of identity that relates tangent and secant together. And I think we saw that in the previous section. I think in 6.2 I did one kind of similar to this. So you're going to do a similar thing. The identity that relates tangent and secant is the Pythagorean identity, right? So there's the Pythagorean identity that says tangent squared plus 1 equals secant squared. In order to get that, you're obviously going to have to square both sides of this equation. But don't do that just yet, because if you square the left-hand side the way that it is, you're going to get a tangent squared, and then a tangent squared term. Then you're going to get a secant tangent term, and then you're going to get a secant squared term. Now, the tangent squared we could rewrite as a secant squared using that Pythagorean identity we just talked about. The issue is going to be with that secant tangent term in the middle. So in order to avoid that, my advice would be move one of these functions over to the other side first, and then square both sides. That way, you avoid having a secant tangent situation. So go ahead and give the video a pause and see if you can work that out now that I've given you abundant hints. Okay, here's my solution. So I'm going to go ahead and move the secant over. You could have moved the tangent over, it wouldn't matter, okay? So don't abandon hope if you moved the tangent over instead of the secant. Okay, now I'm going to square both sides. On the left-hand side, well, that's just tangent squared, 3x. On the right-hand side, I'm going to get a 4, 2 secant 3x, and then right. So when I do the inner, I'm going to get a 2 secant x, and then when I do the outer, I'm going to get another one. So it's going to be minus 4 secant 3x, and then I'm going to have a positive secant squared 3x, right? So you've got to FOIL it. Okay, so now that I've got all of this stuff in terms of secants, I think the easiest thing to do is going to be to rewrite this tangent squared as a secant squared. So let's do that. Okay, so I can rewrite the tangent squared as secant squared minus 1. So this is secant squared 3x minus 1. And then the secant squareds cancel. Now I've just got 4 secant 3x, or 4 minus 4, so secant 3x equals negative 1. So I'm going to subtract the 4 over to the other side, and I'm going to rewrite this as negative 4 secant 3x equals negative 5, right, if I move the 4 over. And then if I divide by negative 4, I get secant 3x equals 5/4. And then I'm practically done, right? In order to get this in terms of sine, cosine, or tangent, I can use a reciprocal identity and call this cosine 3x equals 4/5. And then I can just apply my favorite little rule, right? I can say, all right, so then 3x equals cosine inverse of 4/5 plus 2n pi, or 3x equals 2 pi minus cosine inverse of 4/5 plus 2n pi. And these are not going to give you nice solutions, okay? But in order to finish solving for x, we would divide through by 3 and get x equals whatever cosine inverse of 4/5 is, right? Cosine inverse of 4/5 over 3 plus 2n over 3 pi, or x equals, oh goodness, this is even nastier, 2 pi minus cosine inverse of 4/5 over 3 plus 2n over 3 pi. Okay. I am running out of space here, so I'm just going to kind of cut to the chase. So here are the approximations. So cosine inverse of 4/5 is about 0.64. And 2 pi minus that, 2 pi minus cosine inverse of 4/5 would be about 5.64. So notice that our period got divided by 3. So this is going to generate 3 times as many solutions as you would normally get. So I think in total you end up with 6 solutions here. And I'm not going to walk you through all of that. But what I will warn you of is that some of them are going to be extraneous. Well, maybe not. I don't know. Maybe none of them are extraneous, but you have introduced the possibility that some of them are extraneous due to the fact that you squared both sides here. And anytime you square both sides of an equation, you introduce the possibility that you have introduced extraneous solutions. So the only way to know if they're extraneous is to plug them back in, right? So we could plug in the 0.64, or rather the cosine inverse of 4/5 divided by 3 here to this original equation in black and see if it gives us a true statement. I'm just going to do that out of curiosity. First of all, notice that when I plug it in here, by multiplying it by 3, the denominator will cancel. So really this is just tangent of cosine inverse of 4/5, which you can get an exact value for. But I'm going to let my calculator do the work. So let's see. Tangent of cosine inverse of 4/5 is 3/4. So here I get 3/4. Secant. So I'm going to say 1 over cosine of cosine inverse of 4/5 should just be 5/4, right? Yep, it's 5/4. 3/4 plus 5/4 is 8/4, which is the same thing as 2. So this one checks out, right? It's not extraneous at all. What about this one over here? If we do 2 pi minus cosine inverse of 4/5. So same thing. I'm going to do tangent of 2 pi minus cosine inverse of 4/5. That gives me negative 3/4. So this is a negative 3/4 now. And then if I plug in the same thing to the secant function, so 2 pi minus that stuff, I still get a positive 5/4 when I plug it into the secant function. And negative 3/4 plus 5/4 is what? 2/4, which is 1/2. So I think you get extraneous solutions here. Okay? So those ones are extraneous. So your solution set, I guess, would look like this. We might as well finish it. We've come this far. So your solution set would be like 0.64 plus 2n over 3 pi, where n is an integer, right? Because these ones were extraneous. And this would be all of the solutions. If you wanted the ones between 0 and 2 pi, well then you're definitely going to get 0.64. You're going to get, and then you're going to get 2 more. So that's all I'm going to say about that one. And that's all I have to say about 6.3. Okay.